Looking at Leetcode number 51. It's called N queens. This is a pretty hard question, but we're going to break it down step by step and try to get to a very efficient solution. We're also going to be using a template, a backtracking recursive depth first search helper function that we use as a template. And if you haven't checked out the other videos in this playlist, highly recommend to do that. I'm using the same template to solve pretty much all the questions in this playlist, just to really highlight the importance of using this template when you're dealing with any sort of question that involves permutations, subsets, or combinations. Okay, so here the n queens puzzle is the problem. We're replacing n queens on an n by n board where no two queens can attack each other. So we're given an integer n. We have to return all distinct solutions to the n queens puzzle. So here we can see that none of these queens can attack each other, and we have two different solutions here. A queen can attack on the side or on the top to bottom. So left to right or top to bottom or vertical up or vertical down. Okay, so we can see that there's no other queens placed where they can attack each other. Okay, so let's jump into this on how we're going to solve this. So first, because we're dealing with an n by n board, we don't need to have an n by n in our slate. Okay, we can actually just use an array and use the indices as the rows and then the values as the columns. All right, so what do I mean by that? So let's say we have this n by n board over here. It's 0 to 3, so we can just create an array from 0, 1, 2, and 3. Okay, so our indices will be 0, 1, 2, and 3. And then our values here can just represent the columns. So let's say I want to place a queen at row 0 and column 0. Then this is going to be my rows, and this is going to be my columns. So at row 0, the column I can have is 0, and that will refer to this position right over here. All right. Now, if I change this to 1, all that means is that now our row is still 0, but our column is 1. Okay, if I change this to 3, that just means that our row is still 0, but then our column comes to 3. So that's just how I'm going to represent this board. That way we save on space. We don't need to create an n by n array. We only do that at the end when we push into our result. But for the most part, we can just use an n slate, an array of n as our slate. Okay, so that's one way we can make this a lot more efficient. Okay, so now what do we want to do here? This is a combination problem, and we have to figure out how can we get all the variations of the queens. So now here's the thing. We have to use backtracking, because if we don't use backtracking, it's just like if we try to get every variation of where we can place a queen, the time and space complexity, or the time complexity in particular, is going to get so insane that we won't even be able to do a number beyond 3 or 4, right? So we have to use backtracking here. So let's say we start with an empty slate, okay? So we have 0, 1, 2, 3, okay? And now, what are our options here on this first level of our tree? Where can we place a queen? Well, we can place a queen in the 0th indice, or in the 0 row and the 0th column. We can put 1 here. We can put 2 here, and so on and so forth until we hit n. Okay, and what we want to do here, let me back up here, is when we place 0 here, we want to go all the way down the tree, and every level we want to check, is there a problem? Like, is there a queen that's going to attack it? So let's say we go here at 0. That means we're going to place a queen here in 0. And now we're going to look at our next row. We're going to look where are all the places we can put a queen on this next row. Okay, so let's just kind of step through that. If this is our slate, then what we can do here is we have 0 here in this second index, or in this first index here. What are the values we want to check? We want to check 0, we want to check 1, we want to check 2, and we want to check 3. Okay, so here we can see that 0, we cannot have a queen there. 1, we can't have a queen there. 2, we can have a queen there. All right, so we're going to place 2 there on the slate and then go down the recursive tree. So let me clear this out here. Okay, I'm going to put a 2 here and then move down the recursive tree. Okay, so here, when we're doing, I'm just doing this depth first search to kind of, because if I do it breadth first, this tree is going to get huge. So let's just look at it from depth first search. Okay, so here we're going to have a 2 here. And now on this third indice, we have already placed this queen in 2. So now we have our third queen here. We want to check, can we put it here in the 0th column? We can't. Can we put it here in the first column? We can't, because we're going to have a conflict there. Can we put the queen here? We can't. Can we put the queen here? We can't. We're going to have a conflict. So now we have to backtrack. Okay, so we tried 0 here. We tried 1. Whoops. Tried 0. We tried 1, we tried 2, we tried 3, none of them work, so now we have to backtrack up here. Okay, so let's go ahead and do that. Let me erase this, and this is going to be a little painful to kind of slowly go through all of this, but it's important because it'll make this backtracking make a lot more sense on how this is working under the hood. I'm not going to go through the whole thing, but I'll go through like 1 or 2 solutions in our global result to just kind of hit home the point. Okay, so now we backtracked here and we know that this 2 is not good, so now we have to go ahead and put 3 here. So let's go ahead and put our queen here, and now we check, can the queen come here? No, it can't. Can it come here? Yes, it can. Okay, so we put this queen here, this is going to go down again, and we found, okay, 0, whoops, 0 works here, 3 works here, and then in index 1, a queen can be placed. So let's now go further down our recursive tree and we check, can we put a queen here? No, we can't. Can we put a queen here? No, we can't. Can we put a queen here? No, we can't. And can we put a queen here? No, we can't. So in this level, or this part of our recursive tree, 0, 3, 1, there is no value here that we can put in that's going to create a valid board, so we have to backtrack all the way up here, actually all the way up to here, because none of these work, right? None of these 4 queens can be placed in any way when we start at the 0th index. So now we have to go all the way back up here and increment this 1, and then rinse and repeat. So let's just go ahead and do that. We'll just do this once just to kind of reiterate this, but if it doesn't make sense after this, I highly recommend getting a pen and paper and just like drawing this out. It really does help clear up a lot of this. Let me just make a brand new, or actually no, we won't do that because we have the board here. So let me just clear this out. But yeah, I can't emphasize enough using a pen and paper to kind of solve this out, because it does help a lot of this stuff make more sense. And then once you do it with a pen and paper a few times, then you don't have to actually draw this out every single time. You're just really familiar with that depth first search recursive helper template, then it's not necessary to draw these out, every single time. Okay, so now we got here and we realized that we cannot place this queen here in the 0. Let me move these queens out. Okay, so now let's try placing the queen here. Okay? And so here we're going to have 1 on our slate, right? And now we have to check here on the next iteration, what can we do here? Where can we place a queen where it doesn't conflict? Okay, so we can't place it here, can't place it here, can't place it here, but we can place it here on the 3rd index. So here we're going to put 3 here, then we're going to go down, and now our slate is 1 and 3, and we have to check this indice. Where can we place a queen there? So here we can check, can we place a queen here? We can. Okay, great. So we'll put 1 here, and we'll go down, and now we have 1, 3, 1, and now we have to fill in this last one, and we have to check, can we place a queen anywhere on our board? So we can't place a queen here, we can't place a queen here, but we can place a queen here at 2. So we can fill this in with 2, and now I goes out of the range, we hit our leaf level, okay, and we push this into our global result. Okay, and then at the end, we're going to want to map through our global result and just format this, right? Because in the question, it wants this formatted looking like this, a string with ... So all you have to do here is just map this through and, you know, format this result so it looks like that, which we'll go over. Okay, so that's the idea behind n-queens. Now, time and space complexity, this is 2 to the n times n, or we can look at it as 2 factorial, but it's really hard to judge time and space complexity when you start adding all this backtracking stuff to it. So, you know, there's just a lot of different ways you can kind of calculate time and space complexity. I think in the solution it's 2 to the n times n, or n to the 2n, right? So yeah, it just gets huge. Okay, so let's go ahead and jump into the code. What we're going to do is we're going to follow that template. So we're going to do a global result. Okay, and we'll do result. We'll set this to an empty array. And then we're going to have our depth first search helper. We'll set I, n, and then we'll have a slate. Okay, and so now we have to have three elements to this. We're going to have a backtracking case. We're going to have a base case, and we're going to have a depth first search recursive case. All right, so what do we want to do with the backtracking case? We want to get our last queen. Okay, so we can say let last queen is going to be I minus 1. All right, now we want to iterate through everything up to last queen. We want to check all the previous queens up to last queen and see if we have any conflicts, right? Because just like we were doing here, we have to check the conflicts on every single one of these, okay? So what we're going to do here is we're going to say for let prev queen equals 0, where prev queen is less than last queen, and then we'll increment prev queen. Okay, and now we want to check, do we have a top bottom conflict? Okay, do we have a column conflict? So if column conflict, let's say if column, we have a column case, so what do we want to call this? We want to say, do we have a column conflict? Column conflict. Okay, and the way we want to do this is if slate at prev queen equals slate at last queen, we can return. Right? So let's take a look at what we mean by that. Let's say we have a column conflict. So let me move these queens out of the way. And let's say our slate here is looking like, I'll just write this on the side here. Okay, so I'll just use yellow here. So we have, this is our slate, right? 0, 1, 2, 3. This is our rows, and this is our columns. All right. So here we have 0 and 0 on our slate on row 0, and we have column 0, right? Now let's say we have a queen here, and I'm just going to use this as an example. So let's say at 2 we have a queen. So we have row 2, and then our column is 0. And so because these columns match, right, in our slate at 0, that's our previous queen, and slate at 2, that's our last queen, the columns match, we have a conflict. Okay, and so we're going to return. That's what this line of code is doing right there. Okay, now we want to check if diagonal conflict. We don't need to check a row conflict because we're getting the previous queen up to the last queen. So we're not ever checking in the same row. They're not going to be in the same row because we're doing this by rows. So we have to check if there's a diagonal conflict. So let's take a look at how we would do that, right? So here's our board, okay, and let me clear this out here. Okay, let's go ahead and clear this out. Okay, so we have our board here. Zero, 1, 2, 3. This is going to be our row, and this is going to be our columns. Okay, and we want to check diagonal, right? So let's take a look at what we would have. Let's say we have 2 queens here. So we're going to have a value of, at row 0, our first queen is going to be 0. And then at row 2, we're going to have a queen at column 2. Okay, so this is going to be 2. Okay, and now what we want to check, is there a row difference? What is the difference in the rows? So here we have 2 and 0. What is the difference there in the rows? Okay, the difference is 2. So we have to say row diff is going to equal the absolute value, ABS, of our previous queen minus our last queen. Okay, in this case, what is our previous queen is going to be 0, and our last queen is going to be 2. So our difference here is 2. Okay, and now we want to check our column diff. And this is going to be ABS of slate at previous queen minus slate at last queen. So I'll just say slate at PQ minus slate at last Q. Okay? And so what is that? That is going to be, our slate is going to be, slate at previous queen is going to be 0. It's the value, right? And our slate at last queen is going to be 2. So this is going to be 2 minus 0, which the difference is 2. Now, if those values are the same, then we have a diagonal conflict, right? But let's say we move this queen right up over here. Now, our difference here is going to be 1 on the rows, but our difference is going to be 2 on the columns. And so we don't have a diagonal hit. This is tricky to get your head around. Highly recommend, get a pen and paper, draw this out. That's the logic, but make sure you understand how this logic is working and why it does. Test a few different cases just to make sure you get your head around it. Okay, so what we're going to do here is say let our row difference, so let row diff is going to equal math.abs and our previous queen minus our last queen. Okay, and our column diff is just the values on the slate, so math.abs of slate at prev queen minus slate at last queen. Okay, and if row diff equals column diff, not column dill, column diff, we want to go ahead and return. Okay, so that's our backtracking case right there. Now we want to get our base case. If we make it to the end of the board, if I is equal to n, then what do we want to do? We just want to scan this and throw this in our global result. So we can do result.push, and we can do a slate.slice, and then return. Okay, and now we just have our depth first search recursive case left. And so what do we want to do here? We want to do just for let column equals 0, column is less than n, column plus plus. We just add this column to the slate, so slate.push column. We call our depth first search recursive. We increment I. Pass in n, pass in our slate, and then pop this off our slate. Okay, so that's it for our main function. All right, it's not too bad. It's just this part right here. You really have to step through this and you know, make sure you design the right strategy on the backtracking case. Okay, so now we're going to call depth first search. We'll pass in 0 as our I, pass in n and an empty array on slate. And then what we'll do is we'll return, because we have to format this. We can just do result.map, okay, and then we'll get a board. Then we can do a helper function called format board and pass in our board. And then let's just go ahead and write out this helper function. I'm going to zoom out here so it's all visible. So we'll have format board. This will take in a board. Okay, and so now we want a formatted board, so we can I'll just call it result. So we'll just say let result equal an empty array, and then we can say for let column equals 0, column is less than board.length, and then column plus plus. And now here, I'm not going to go through the logic of this. All we're doing is, you know, we're getting the result that's looking, you know, like this. It's like a slate with just one array. We just need to convert that into this right here. So I'm not going to go too much into logic, but I think it'll make sense once you see the code. So here what we're going to do is we're just going to say let new row equal new array, and then this will be the size of board.length, and then we'll fill it with periods, okay? And now what we're going to do is at the index of new row, at board of column, we're going to set that to the queen. Okay, and then we're going to push this into our result. So we'll do result.push, and we're going to join it because here they want it joined. So we'll do new row.join. Okay, and then we'll go ahead and return our result. All right, so that's the code. Let's run it, and yeah, you can see it's super efficient, right? Like we're getting 94% on time and 98% on space. Like it's really, really efficient to do it this way. And I think one of the key takeaways here is, you know, obviously step through this, use this template, this backtracking template. It allows something that seems initially so impossible, like n-queens, like how do you figure this out? But when you apply this template to it, all you really have to figure out is this backtracking case, right? You just have to think about it. You just have to look at it, you know, kind of work through it. The other clue here is that because we're using an n by n board, you can use a slate like this and just make it a lot more efficient than creating a board on every single recursive call. And the cool thing is once we solve this, if you look at n-queens 2, I'm just going to copy this code here. Okay, and I think n-queens 2 comes up. Let me type in n-queens 2. Okay, and there we go, n-queens 2. I think I already solved it, but let me clear it out here. Okay, so you can see here if we just type in the same code here, I think it's total n-queens. And all we have to do is this result.map.board, how we're mapping it, we just return result.length. Because all this is asking is how many boards can we have, right? And you can solve it, you know? Just making that small little change in the code, you can pretty much solve that one too. Okay, so that is n-queens 1 and 2. This is a hard question. I would spend some time with this. You know, it's hard to just understand this just by watching a quick video or even just reading through a quick solution. The best idea is just, the best suggestion is to just get a pen and paper, draw it out, really understand what's happening at each step, and try to have a clear command of how to use this template. Once you know how this template is creating a recursive tree, how you're doing depth first search, and how you can add these backtracking constraints, then you don't have to focus on how to get all the combinations. You just have to focus on how to figure out what the constraint is. And that's the tricky part about this one, is I think just figuring out how to get that constraint. But even that is not too bad, once you kind of stare at it, you can kind of see like, okay, there's an efficient way to do this. Okay, so that is N Queens. Hope you all enjoyed it, and I will see everyone on the next one.